Okay, in our previous video, we talked about continuous function between two topological spaces. In this video, we're going to talk one more type of special function between two topological spaces, which is called homeomorphism. Okay, homeomorphism. Let me give you formal definition of homeomorphism, and then I will give some examples. Let's say x and y are topological spaces. And let f from x to y be a bijective function, such that both f and the inverse f inverse from y to x are continuous, then the function f is called homeomorphism. It's called homeomorphism, and the topological spaces x and y are called homeomorphic or topologically equivalent spaces. Okay, so this is the formal definition of homeomorphism. Let's say x and y are two topological spaces, then a bijective function from x to y is called homeomorphy. It's called homeomorphisms if both f and the inverse, since our function is bijective, so the inverse exists. This function f is called homeomorphism if the function f and its inverse are continuous. And if f is a homeomorphism between those two topological spaces, then x and y, they are called homeomorphic. So if x and y are homeomorphic, that means they are similar. Okay, so you can see from the definition, if you simply have a function from a topological space x to y, then in order to be that function a homeomorphism, these are the three things that function should satisfy. The first one, f, it has to be bijective. F should be bijective. Bijective means it has to be both injective and surjective. So it has to be injective and also surjective. So that's the first condition. If you simply have a function between two topological space, in order to be that function homeomorphism, the first thing, the function that function have to be a bijective function, and the second one is f has to be continuous, or this function should be continuous, and the third one, not just the f inverse also it has to be continuous. Okay, if a function between two topological spaces satisfy those three conditions, then the function is called homeomorphism. And if a function is homeomorphism, then those two topological spaces, they are topologically similar. Okay, now next I'm going to give you some example of homeomorphism. But before that, just let me mention one thing. So you guys have learned about homomorphism. You guys have learned about the homomorphism in linear algebra and also abstract algebra, and then also in proof classes. So that homomorphism is not same as the homeomorphism. So don't be confused with homomorphism and homeomorphism. Okay, homomorphism and homomorphism that you learn in fundamental of mathematics, which is proof class, linear algebra, abstract algebra, these are different than the homeomorphism that we are learning in this video. Okay, so this homomorphism and homeomorphism, these are the two different things. Okay, and so I think you have also learned about the isomorphism, maybe homeomorphism and the isomorphism. Somewhat you can say, if you compare, they have the similar property, but not the homomorphism and homeomorphism. So don't be confused with homomorphism and homeomorphism. These are two different things. Okay, all right, so now I'm gonna give you some example of homeomorphism. And first example number one. Let's say let's consider R, which is the set of real number with standard or order topology. Let's say we have a set of real number with standard or order topology, and consider a function f from R to itself. Okay, in both R, domain and codomain, both R's they are on with standard or order topology. So basically, in order topology, the basis elements are open interval. Okay, consider a function f from R to R defined by this relation 3x plus 1 for x in R. So we have a function from R to R, and both R, they are with the standard or order topology, and we have defined a function f with this relation. Now here, this function f is a homeomorphism. So we are claiming this function is a homeomorphism. So as I said earlier, if this function is homeomorphism, it should satisfy those three conditions. The first one is bijective. So this function, it has to be bijective. And to check whether this function is bijective or not, it is either you can check algebraically, or you can use a graph as well. So let's say if you are if you want to check this function is bijective or not, the first thing you have to do, so this function is injective, and also it has to be surjective. In order to show this function is injective, what you need to do is, what you can do here is, a function is called injective if the two images are equal, then their pre-image should be equal. That means suppose x1 and x2, these are the two elements in the domain of this function, such that their images such that their image of x1 is f of x1 is same as f of x2, then we can say this function is injective if the pre-image of f of x1 and pre-image of f of x2, which are x1 and x2, if they are the same thing. And to show that it is easy, just you use the definition of f of x1. F of x1 is 3x1 plus 1. So I'm just using this definition. And f of x2 is 3x2 plus 1. Just simplify. Then you're gonna get x1 equal to x2. Now you can see here. Here we took two arbitrary elements in the domain of our function with their images are same, and we found that the pre-images are also the same thing. That means which implies that f is injective. So f is injective, and also if our function is bijective, it has to be surjective as well. So to show the surjective, so what you can do is you can show that for every element in codomain, there exists an element in the domain such that so for example, let's say every element y in the codomain, so there exists an element x in the domain R such that f of x, it has to be y. So this thing, it tells us that the range of your function and the codomain is same. If you have a function whose range is same as the codomain, then the function is surjective. So you can we need to show this condition is true. Okay, this condition is true. If this condition is true, then the function is surjective. So to show this condition is true, so as suppose let's take an arbitrary element in the codomain. Let's call that arbitrary element is y. Suppose y is in R such that f of x equal to y. Now we need to show that this guy x is in the domain or is a real number. Okay, suppose y is in R such that f of x equal to y. Then by definition of our function f, we can say that f of x, which is 3x plus 1 equal to y, and if you simplify this one for x, is going to be y minus 1 over 3. So now since y is a real number, if you subtract 1 from real number and divide by 3, that is obviously is a real number. So here we just showed that if we take arbitrary element in the codomain, for that arbitrary element we can find an element in the domain which is y minus 1 over 3 such that f of x is y. So this implies that, so if you want to write down this one, you can write down like this one, like this. Thus for every y in R, this R is our codomain or the second set in our function. Thus for every y in R, there is an x which is y minus 1 over 3 in the domain R, for which f of x equal to y. So that means we just showed that range and codomain are equal, so which implies that f is surjective. Since our function is both injective and surjective, so the given function f is bijective. That's the first condition. That's the first condition for the function to be homeomorphism. And you can see also you can check this function is bijective using the graph like this one. So if you graph our function is f of x equal to 3x plus 1, you can graph this function. Graphing this function is not hard. It's easy thing. Just if you graph this function, the graph is gonna be like this. Since y-intercept is 1, so it crosses the y-axis or this vertical line at 1, and then you can see x-intercept is negative 1/3, so it will crosses the x-axis or the horizontal line at negative 1/3. So the graph of our function is this one, right? This is the graph of our function. And now you can see here, if you use that horizontal line test, is injective. That means if you draw any horizontal line, that horizontal line intersect the graph 1, so it is injective. And then also, since the codomain of our function is the real number, is the set of real number, and you can see the range of our function is keep going down and down, is keep going up. So range is also from negative infinity to positive infinity. So the function is bijective, so both injective and surjective. So instead of proving function algebraically, you can use graph to show that function is bijective. Okay, that was our first condition for the function to be homeomorphism. And the second one is the function f, it has to be continuous. Okay, and here our function f is continuous. Our function f is continuous since, so remember, our function is from set of real number to set of real number with the standard topology. And this function is and the function is defined by this relation f of x equal to 3x plus 1. And we know that this function is continuous if the inverse image of each basis element for the standard topology on this R is open in R. And we know that the basis element for the standard topology on R, they are the open interval like this one. So these are the basis element in the for the standard topology on R. So the inverse image of that guy, the inverse image of this open interval, it has to be, the inverse image of this basis element, it has to be open in R. And now we can find the inverse inverse image of A. So if you plug in A for here and solve for x, so you're going to get the inverse image of A, that is going to be A minus 1 over 3. Just you plug in A for f of x here and solve for x. So the inverse image of this basis element is gonna be, inverse image of A is going to be A minus 1 over 3, and the inverse image of B is going to be B minus 1 over 3, and this open interval. So, and if you have an interval like this one, then that is obviously going to be open here in when you have the standard topology on R. And under the standard topology, open set R, basically these are the open interval. Now here we have just seen that inverse image of basis element is an interval of this form, and which is an open set in R. So our function f is continuous since the inverse image of a basis element, inverse image of a basis element AB of the standard topology on R is this open interval, and obviously which is open in R. So our function f is continuous, and so the given function also satisfies the third condition, and also it has to satisfies the second condition. Also it has to satisfy a third condition, and third condition is the function f inverse, the inverse of this function, inverse of f of x equal to 3x plus 1, it has to be continuous. F inverse is continuous. Okay, so to check whether the inverse is continuous or not, the first thing we need to find the inverse of this function, and you can find the inverse of this function. So you have learned how to find the inverse of function, inverse of bijective function in lower level math courses like in college algebra. So if you find the inverse of this function, you will get this guy, which is going to be x minus 1 over 3. So it is easy to check that. If you define the function with this relation x minus 1 over 3, that's going to be the inverse of 3x plus 1. So here, let me just write down this one. It is easy to check. It is easy to check that f negative 1 from R to R are defined by f negative x equal to x minus 1 over 3 is inverse of f. Okay, all right. So we found the inverse of our function, and then this function, it has to be continuous. Again, our function, you can see the inverse is from R to R. Both R, they are under the standard topology. So this inverse is continuous if if the inverse image of a basis element for the standard topology on R is open in this R, then we can say that this function is continuous. And for that one, so we got the inverse function. Now we can say that f negative 1 or f inverse is continuous. It's continuous because the inverse image of a basis element, inverse image of the basis element AB of the standard topology on R it's going to be, so if you plug in A for this f inverse x and then solve for x, you're going to get 3a plus 1, and for b 3b plus 1. So the inverse image of AB for this function is going to be this interval, and which is obviously open in R. So that f inverse is also continuous. So here we have proved that f satisfies all three conditions for a function to be homeomorphism. So finally we can conclude that f is a homeomorphism from R to itself. Okay, so this is an example of homeomorphism. Now let me give you one more example. So the first example, it was kind of obvious example of a homeomorphism. Now let me give you the next one. For the next one, let's say R is a set of real number with standard or order topology. Okay, order topology, because the standard topology and order topology, they coincide on the set of real number. And let's say let's consider negative 1 to 1. This is the subset of R with order topology, order or subspace topology. So we have two topological space. One of them is R, set of real number with the standard or with order topology, and the other one is subset of R, which is negative 1 to 1 with the subspace topology. So if you find the subspace topology on negative 1 and 1 on this interval, and also if you find the order topology on this interval, they are the same topology. So let's consider this subset of R with the order topology or the standard topology. Basically, R with the standard topology, the basis elements are like this interval, and then on negative 1 to 1 with the order topology or subspace topology, these are obviously the open interval of this form. Okay, now here let's consider a function. Let's consider a function f from this interval negative 1 to 1 or from x to r, defined by this relation f of x equal to tangent 1/2 pi x for x in this open on this interval of negative 1 to 1. So we have a function f from this interval negative 1 to 1 to r, which is defined by this trigonometric function tangent. Okay, all right. So here this function is going to be a homeomorphism between this interval and r. So in order to this function, or in order to be this function homeomorphism, this function should satisfy all three conditions. The first one, the function has to be bijective. So like I mentioned in the first example, you can show this function is bijective algebraically or by using graph. So let me use the graph here. So just let me remind you the graph of tangent function, or tangent 1/2 pi x between negative 1 and positive 1. You can see here the domain of our function is simply that interval from negative 1 to positive 1. So it's from negative 1 to positive 1. So I'm sure you guys have seen the graph of tangent function in your trig class. So if you graph this tangent 1/2 pi x, then the graph of your tangent function is gonna be like this one, with the asymptote at negative 1 and positive 1. So this is the graph of this is an asymptote, vertical asymptote, and this one is another vertical asymptote at 1 and negative 1. And so this one is the graph. This is the graph of your function tangent 1/2 pi x. Now you can see here. So if you use the horizontal line test, the horizontal line intersect the graph just once, so it is injective. Okay, it is injective from this graph using the horizontal line test. And for the surjective, the codomain and the range of your function has to be same. And you can see the codomain of our function is R, which is the set of real number. And you can see here the graph of our function is keep going up and also is keep going down. That means the range is from negative infinity to positive infinity. So range and codomains are the same thing. So function is surjective as well. This is which we can see from the graph. Range and codomain are the same thing. So we can conclude that our function is bijective. Okay, that's the first. So our function satisfy first condition. The second condition is f has to be injective, and in fact f has to be continuous, and in fact f is continuous. Our function is continuous. And we know that function is continuous if the inverse image of each basis element is open in X. So the basis element of basis element for the standard topology on R, they are going to be in this form AB. And if you take the inverse image of this guy, so if you take the inverse image of A, so what you can do is to find the inverse image, just you plug in A for this guy and solve for X. So if you do that one, then you're going to get 2 over pi tangent inverse X, sorry, not X, is A. And if you find the inverse of B, then you're going to get 2 over pi tangent inverse B. That is what you're going to get if you find the inverse image of A and B. And so this implies that the inverse of this interval is an interval of this form. And obviously this interval is open in X because we are considering order or the subspace topology on this interval -1 to +1. And the open set in this interval if you are considering the order topology or subspace topology, open set in this interval, they are all in this form. So we found that the inverse image of a basis element is open in X, so that our function f is continuous. Okay, so just let me write down so what I just described here. So f is continuous since the inverse image of a basis element AB for the standard topology on R is open in -1 to 1, so that this function, the given function, is continuous. Alright, so our function also satisfies the second condition as well, and then also it has to satisfy the third condition, which is the inverse of given function has to be continuous. Okay, the first thing we need to find the inverse of given function. So f inverse is continuous. So we can find the inverse of given function. Our function is f of x, which is tangent 1/2 pi x. So that is our inverse function. Sorry, that is our function f of x equal to tangent 1/2 pi x. And you can compute the inverse of this function. If you compute the inverse of this function, you're gonna get 2 over pi tangent inverse x. So that is going to be the inverse of this function. And it is easy to check that if you define the function from R to the interval from -1 to 1 using this relation, then that function is going to be inverse of the given function. So just let me write down this thing here. F inverse is continuous. So like I said, to show this function is continuous, the first thing we need to show that it is we need to find the inverse of this function, and which we just computed here. So it is easy to check that f inverse or f -1 from R to x is the interval from -1 to 1, are defined by f inverse x equal to 2 over pi tangent inverse x is the inverse of f, and it is it is continuous as well. It is continuous because the inverse image of a basis element for the topology, for the subspace or the order topology on X, basis elements, they are like the open interval of this form, because we have a subspace topology or order topology. And if you have order topology, and if the set does not have like both least and greatest element, then the basis element, they are simply the open interval like this, because the inverse image of a basis element for a order topology, for the order topology or subspace topology. In this case, subspace topology and the order topology, they are going to be the same thing. The inverse image of a basis element AB for the order topology on R, sorry, not on R, on X is the interval from -1 to +1, is open in R. Okay, so our functions satisfy all three conditions for the homeomorphism. So thus we can conclude that, so thus F is homeomorphism. Homeomorphism, and this interval -1 and R are homeomorphic. That means the interval from -1 to +1 and the real line, topologically they are similar. Okay, that's the meaning of these two spaces are, these two topological spaces are homeomorphic. If they are homeomorphic, topologically they are identical. Okay, so now let me give you one more example. Example number 3. So let's discuss those continuous map between the continuous map from lower limit topology to the standard topology that we discussed in our previous video. So if you remember, in our previous video we discussed two maps or two functions. One of them, it was from lower limit topology to the standard topology on R, and the function, it was like the identity function, and which was the continuous. And the other one was from standard topology to the lower limit topology, and again the function was identity function, but that function was not continuous. So now let's talk about those two functions here. So consider a function f from lower limit topology on R to the standard topology on R are defined by f of x equal to x. And we have seen in our previous video, this function is continuous, and obviously this is bijective because this is an identity function, right? So then f is bijective and continuous. This function is bijective and also continuous. Then the inverse, instead of then, let me just say, then f is bijective and continuous, but the inverse of this function, which is from R standard topology to the lower limit topology, defined if we defined a function from standard topology to lower limit topology using the same relation, then that is going to be inverse function, because our function is identity function and the inverse of identity function is itself. So then f is in bijective and continuous, but the inverse f from R to RL are defined by x equal to x is not continuous. We have seen in our previous video, if you defined a function from standard topology on R to lower limit topology using this relation is not a continuous. So in this example, so what we saw is we have a function f which is bijective and also continuous, but its inverse is not continuous, so this function is not homeomorphism. That means you can have a function which is bijective continuous but not homeomorphism. Okay, so of bijective continuous function, or you can say like that, a bijective function can be continuous without being homeomorphism. So from this example we can conclude, so let me write down as a note, a bijective function can be continuous, which we have seen here. A bijective function can be continuous without being a homeomorphism. So that means if you have a bijective continuous function, is not mandatory that function has to be homeomorphism. All right. So far I gave you the definition of homeomorphism, and then I gave you some example of homeomorphism, and also I gave you an example of a bijective continuous function which is not homeomorphism. Now you can see here this the continuous function, they are very important in topology, because we use the continuous function to check whether the given topological spaces are homeomorphic, or given topological spaces are topologically similar or not. That's why the continuous functions are important in topology. Since the continuous functions they are very important in topology, next I'm going to give you some functions which are continuous. Okay, so I'm going to give you some functions which are always continuous. So let me give those functions, the list of those functions is a theorem, and I'm not going to prove this theorem, but if you are interested in proof, you can take a look in Munker's book. And the statement of theorem is this one. Let's say x, y, and z, these are the three topological spaces. We have three topological spaces. Then the first type of the continuous function. This theorem, it tells us that the constant functions are always, if you have a constant function between two topological spaces, then that function is always constant. So if you want to write down this more formally, so you can write down this as a statement like this. If f from x to y maps, if this function maps all x into if this function maps all of x into a single point y0 in y, then f is continuous. Okay, so if you have a function which maps entire domain into a single point a single point in codomain, then that function is called constant function. That's the definition of constant function, and I'm sure you guys have seen the definition of constant function in lower level math classes. So here we have a function f that maps entire domain x into a single point y0 in codomain. So we have a constant function, and this constant function this constant function is constant. It's continuous. So this is the first type of the function, first type of the continuous function that gives this theorem. Constant function is always continuous. And the second one is second type, which is called the inclusion. So inclusion are also continuous function. Now what do you mean by inclusion? Okay, if A is a subspace, if A is a subspace of X, then let's say A is a subspace of X, or A is a subset of X, and if you define a map from A to X, then that is called the inclusion. Okay, then the inclusion, so we have a subset of X, then you define a map from A to X, from a smaller set to a bigger set, and the smaller one is the subset of the bigger one. If A is a subspace of X, then the inclusion function, which we usually denoted by J, I is for identity, J is for inclusion, A to X is continuous. So this is the second type of function that's gonna be always continuous. Inclusion function functions are continuous. Constant functions are continuous. And the third one is the composite of two continuous function is also continuous. So if f from x to y and z from y to z are continuous, then the composition of this function g composite f, which is from x to z, is continuous. So that's the third type of continuous function. If you take the composition of two continuous functions, then you can construct the new continuous function. Okay, and the last one is restriction to domain. So if you have a continuous function and if you restrict the domain of that continuous function, the resulting function is also going to be continuous. Let me write down. So if f such that f from x to y is continuous, we have a continuous function, and if A is a subspace of X, then if you restrict the domain of your function f to A, so the domain of original function is X. If you restrict the domain of this function to a subspace A, then this function is going to be from A to Y and it's continuous. Okay, it's continuous. So this is another way of constructing continuous function. If you restrict the domain of continuous function, the resulting function is going to be continuous. That's the last one. Third one, if you take the composition of two continuous function, then you can construct the new continuous function. And if you take the inclusion map, that's gonna be also the continuous function. constant map or constant function, they are also going to be the continuous function. So these are the different way of constructing continuous function. Okay, like I said earlier, I'm not going to give a proof of this theorem. If you are interested in proof, you can take a look in Munker's book.